Now in this video we will be solving this question which says a consumer faces the following utility maximization problem where you have to maximize u, a function of x comma y, which is 100 minus e to the power minus x minus e to the power minus y, subject to px plus qy is equal to m, where x is positive and y is positive. Here P and Q are per unit prices for good X and Y respectively, and M is the money income. We have to find the necessary conditions for the problem and solve the two demand functions. X is equal to f, a function of p comma q comma m, and y is equal to again a function of p comma q comma n by using a Lagrangian method. So let's quickly revise the necessary condition, which says a necessary condition for a differentiable function to have a maximum or a minimum at the interior point x0, y0 of its domain is that x0, y0 is a stationary point of f. That is, the first order partial derivatives takes the value of 0 when evaluated at this point, that is x0 and y0. And let's see what is your Lagrangian method, which says to find the solution of a problem which is maximize or minimize fxy subject to gxy is equal to c. We have to proceed as follows, where we first write down the Lagrangian function Lxy is equal to fxy minus lambda minus gxy minus c, where lambda is a constant. And then you differentiate L with respect to x and y and equate the partials to 0. That would give you three equations, which is f prime x xy is equal to lambda g prime x xy, f prime y xy is equal to lambda g prime y xy, and gxy is equal to c. And lastly, you have to solve these three equations for the three unknowns x, y and lambda. That is, you have three equations and three unknowns, and you have to solve for the unknowns. So coming back to the solution, you have to maximize uxy for x and y subject to this constraint. Setting up the Lagrange, which means your L is equal to 100 minus e to the power minus x minus e to the power minus y plus lambda m minus px minus qy. And let's order the first order conditions, which are your necessary conditions. For that, we have to differentiate the L with respect to x and y. So differentiating L with respect to x, I'll get del L by del x is equal to minus of e to the power minus x multiplied by minus 1 plus lambda minus p is equal to 0, or e to the power minus x minus p lambda is equal to 0. So this is my first condition. And similarly, differentiating L with respect to y and equating it to 0 in order to get the stationary points, I get that minus of e to the power minus y minus 1 plus lambda multiplied by minus q is 0, which will give me the equation e to the power minus y minus qy is equal to 0. And when I differentiate L with respect to lambda and equate it to 0, I will get that m minus px minus qy is equal to 0, or px plus qy is equal to m, which was your third conditions. Now you have these three equations and you have three unknowns. So let's solve them. Your first equation was this, which is e to the power minus x minus lambda p is equal to 0, which can be rewritten as e to the power minus x is equal to lambda p. So let's take a log, which is a natural log, so which is essentially ln, because we have here e. So that's why we are taking ln, so that by using the property of log, which is ln of e is equal to 1, I can get rid of this e. So I get that ln e to the power minus x. So what I am doing here is I am writing it as ln e to the power minus x, which is equal to minus x by using the property of log, which is log of a to the power b is b log a, and your log a is 1. By taking the log, I get that minus x is equal to ln lambda p, or x is equal to minus ln lambda p, or ln lambda p to the power minus 1, again by using this property. So your x star is ln 1 divided by lambda p. Similarly, e to the power minus y minus lambda q, by doing the same calculation as above, we can get that y star is equal to ln 1 divided by lambda q, and we already have that px plus qy is equal to m. So let's substitute the value of x and y into this equation. I will get that p ln 1 divided by lambda p plus q ln 1 divided by lambda q is equal to m. So again, for solving this, I will be using these two properties, which is log of mn is equal to log m plus log n, and log of m divided by n is log m minus log n, which will be p multiplied by ln 1 divided by lambda multiplied by 1 divided by p plus q ln 1 divided by lambda multiplied by 1 divided by q is equal to m. Now this product can be rewritten in this form, by using the property 6 we discussed above, and this can also be rewritten like this. So that will give me p multiplied by ln 1 divided by lambda plus ln 1 divided by p plus q ln 1 divided by lambda plus ln 1 divided by q is equal to m. So simplifying this, I'll get p ln 1 divided by lambda plus p ln 1 divided by p plus q ln 1 divided by lambda plus q ln 1 divided by q is equal to m. So clubbing this term and this term together, I will get that ln 1 divided by lambda multiplied by p plus q. And this can be written as, by again using the property we discussed above, which is p ln 1 minus ln p, and this can be written like this again by using the property we discussed above, which is q ln 1 minus ln q is equal to m. Now ln 1 is 0, so you get that, and this is also 0, so I will get ln 1 divided by lambda p plus q is equal to m p ln p plus q ln q, by taking this term and this term on the right hand side. That will give me ln 1 divided by lambda is equal to m plus p ln p plus q ln q divided by p plus q. Now substituting this back into 4 to get x star, that is by substituting this value into this to get the value of x star, as ln 1 divided by lambda p can be written like this, and which further can be written like this, and we have to substitute this value with this value. So by making the substitution, I will get that m plus p ln p plus q ln q divided by p plus q plus, and this can be written like this, ln 1 minus ln p, and as you know that this is 0, so I will get that m plus p ln p plus q ln q divided by p plus q minus ln p. Now taking the LCM, I will get that x star is equal to m p ln p plus q ln q plus p minus ln p ln p minus q ln p. So this and this gets cancelled. I am only left with x star is equal to m plus q ln q minus ln p divided by p plus q, and this can be written like this. So x star is equal to m plus q ln q divided by p plus q. So this is the value of your optimum x star, which is a function of p, q and m. Similarly, we can find the value of y star, which was ln 1 divided by lambda q, which can be broken down into this term. And by making the substitution for the value of ln 1 divided by lambda, which is m plus p ln p plus q ln q divided by p plus q, and this can be rewritten like ln 1 minus ln q, and ln 1 is 0, so this gets cancelled out. This is nothing but this just same steps we are repeating as we did for x star. So by doing all the calculation, your y star would be m plus p ln p divided by q divided by p plus q. As you can see here, your y is a function of p, q and m. Now your second part says that what happens to the optimal value of xy if per unit prices of both the goods and consumer income are doubled. Let your p hat be 2p, q hat be 2q and m hat be 2m. Earlier your optimal value was this, so which was m plus q ln q divided by p plus q, and after making the changes, that is after your prices and money income are doubled, let's make the substitution and see what happens in your x. That would be 2m plus 2q ln 2q divided by 2p divided by 2p plus 2q. Overall, you will see that here your 2 and 2 gets cancelled, and after I take the 2 common, that would be m plus q ln q divided by p whole divided by p plus q, and you have 2 common from the numerator and 2 common from the denominator, which will get cancelled. So your x hat is equal to x star, where your x hat was new demand. Similarly, your y hat will be equal to y star, x hat is equal to x star and y hat is equal to y star. Your optimal values remains unchanged.